All right, so we talked a little bit about, in the last video, electronegativity. We reviewed electronegativity. Okay, so let's go to work, shall we? Okay, we have hydrogen and we have chlorine. That's the one I always start with, correct? And when it bonds, here you have one electron there for hydrogen, and you have one here, 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 here. You have 7 for chlorine. And it forms a bond. Let's call it a covalent bond. We're going to do covalent bonding, okay? Ionic bonding is easy. It just takes it, and we'll do ionic bonding, but I want to look at this. So here we have a bond that forms, correct? Yes or no? These are actually Lewis dot structures, if you want. It's a Lewis dot structure. I just made X's just to differentiate them from the dot, okay? So here is your atom, your molecule. This is called hydrogen chloride. Now, this is interesting because in the gaseous state, this is a covalent bond. In the aqueous state, it looks like this. It's ionic, where you have this, it pulls it apart. This actually is hydronium. Okay, remember hydronium or not? In other words, the water, you have 2 electrons here, two pairs of electrons there, it kind of pulls it apart. For kind of a reason that we're talking about here. This reason is the same reason as we're going to talk about here. Okay, so just keep this in mind. Okay? Just keep that in mind as we talk. Okay? Now, so this is what we have, hydrogen chloride. So, do you understand that chlorine has an electronegativity of 4, and hydrogen has an electronegativity of what, like 2.2? I'm guessing. Anybody? You have your sheets. You can take a sheet if you don't have one. You have them, right? But just, you know what? Pass out some sheets over there. Pass out some data booklets. Everybody can borrow a data book. Just put it back at the end of class, okay? We have plenty of data books. So this is what you have, okay? That's what you have. Now, chlorine is significantly more electronegative than hydrogen. So the bond, we'll say, looks like this, okay? That's what the bond looks like. It's like a cloud, of course, right? Right? Now, basically, that's sort of like a sigma bond, right? What are the longest bonds? They're basically sigma bonds, okay? You don't really talk about sigma bonds until you talk about hybridization, but we're going to call it a sigma bond just because we want to be rebellious. Sigma bond is just a bond with an S shell, you know. So it's not really a sigma bond, I guess, but we're going to just say it's sort of like that, but it's not. All right, so do you see that this has 1 proton and 1 electron? Do you see that? Right? You see that? Yes or no? Yes? Okay, good. Well, do you see that this has 17 protons and 17 electrons? You see that? Right? Now, it's sharing one of the electrons. You see that? It's kind of sharing one of the electrons. So this has 18 electrons and this has 2 electrons. This is like helium and this is like argon. All right? We okay with that? All right, now. But you see that this is shifted. You see that cloud, that bond, has a shift in electronegativity. Do you see that? Yes or no? I need black. Oh, here's black. All right, so do you see that this has maybe 1 electron plus maybe like half an electron? See that? If you're talking about accounting and talking about actual charge, is that a reasonable model? It may be a quarter, it may be 3/4, but it's less than a -1. Do you agree, Ling Ling? I mean, the chlorine is pulling that bond, man. It's pulling it over there. So it's going to be a little bit less than 1 electron, isn't it? We'll say it's half. Do you get that or not? Ling Ling, you look troubled. I don't want you to look troubled. Look, how many electrons does hydrogen have in the ground state? 1 electron, right? And it's sharing it with chlorine, right? But chlorine is kind of hogging both electrons to itself, to the point where it might snap. It doesn't. In the gaseous state, it stays hydrogen chloride. It stays covalent. But do you see that if you look at the accounting, it's not +1 plus a -1, is it? It's +1 plus a little bit less than maybe a half of negative. So do you see that we could say that this side, that means partial, Greek letter, partial, Greek letter delta, right? This means change. That's capital delta. Means partial. Lowercase delta, that's a capital delta, and it's a lowercase delta, right? Uppercase delta, lowercase delta, yes? Means partial, so we can say it has a partial positive charge. Can we say that? Does anybody have a hard time with that? It sounds like I'm making this up as I go along, I know. But I'm trying to use a model, and I'm giving you rules, right? About electronegativity and attraction and bonding sites, right? Am I consistent with the model that I've been making? I am. I'm consistent, aren't I, Johnny? Yeah, I'm consistent. So that's partially negative. Wouldn't you say that that's partially positive? Wouldn't you say that's partially negative? Now, what you do is, that's called a polar bond. That's what that's called. When you have a shift in the bonding cloud, it's called a polar bond. And the way you represent that polar bond is with what we call a dipole moment. That's the dipole. It has a dipole moment. It's a word. You don't like the word? I don't care. Reinvent chemistry and come up with your own language if you have no life. Okay? It's called a dipole moment. It's a shift in the cloud. Make sense? This means it's polar. Polar covalent bond. Yes? So a bond can be polar or non-polar. Correct? Make sense? Now, I drew water up here, didn't I? Yes? Let's look at water. Water's a little bit funky.
Wait, no, I don't think that's the exact structure for water, because water is supposed to be H2O. And then
Right, but when you put this in water solution, this water rips apart that hydrogen, rips apart that bond, and becomes hydrochloric acid. And you get this in the form of that and that. Two separate species. Species, whatever. Depends if you're Richard Attenborough or not. Yes?
Why are the chemicals called species when they're not live?
It's just the application of a word. Species can mean like a bunch of things. I mean, it can be used as a chemical term. Look up the word. See what the word means. I oftentimes use words and I don't, do you ever, anybody ever ask you directions to someplace and you really can't give them? You know how to get there, but you can't explain it? Yeah, sometimes I do that. Okay, so can I erase this? Okay, I want to erase this. Okay, because I want to now turn our attention to you have a polar bond, but how can you have a polar molecule? Make sense? Okay, so what happens is this. This is what water looks like. That's 109.5-ish, that angle, okay, ish, okay. And you get these electrons here, okay. Now, oxygen is more electronegative than hydrogen, isn't it? Yes or no? Okay. and you get these shifts. And the shift is in the direction of the more electronegative element. That's how you know the direction of the shift. You have to have an electronegativity table with you. Right? Yes?
What do you mean by shift?
Shift means a shift in the cloud. Remember, I had a shift in the cloud because oxygen is more electronegative than hydrogen, so it's going to hog some of the electrons. So your cloud is going to look like this. Right? It's asymmetrical distribution. Ooh, that sounds good. Asymmetrical distribution. It's asymmetrical. 2 M's? 2 M's. Okay. Asymmetrical distribution of charge. Okay? Yes? Dipole moment. Okay? I was wondering what that noise was. Okay, so do you see that you have this dipole moment, right? Yes or no? Okay, now, can I erase this? Okay? Now, so you have this, hydrogen, oxygen, hydrogen. You have these electrons, you have this unbonded pair up here, okay? Yes? And what happens is you get this partially negative charge here, partially, wrong way. Partial positive charge. This is partial negative charge, partial negative charge. See? You see that? Yes? So really what you have is that. Partial negative, partial positive, partial positive. Right? Yes? Okay. Right? So, look at what you have. You have this. Right? And then you have okay? Right? Turn around and do this with somebody. Hold hands with them. Okay, find somebody. 1, 2, 3, 4, 5, 6, 7. Okay, hold hands, okay, and put your arms out. You gotta get close. You gotta get close to each other. Put your arms like this, all right? So they're at an angle of about 109.5, right? Right? Now, you're gonna push along this vector. You're gonna push along that. That's the direction you're gonna push. So porcium, you're gonna push like this, okay? And you're gonna push like this, right? You get it? You ready? 1, 2, 3, push. You're going to go like that, right? Guys, you got to get closer because you're like, right? So aren't you going to go up? You're not going to push like this. You're not going to push this way. You're going to push this way, right? So you're going to go, yeah, see how you're rising? So think of it in a sense that they're force lines. And you have this resultant vector. That's what you would say in physics. You studying physics? Anybody studying physics? You study mechanics, right? Vectors. It's a result. It's like a resultant vector, really. So you have this little bit of a resultant vector because of these two dipoles. You get it? So if you have in a molecule, what basically defines a molecule? What does a molecule have that other particles or other species does not have? Yes?
It's made up of several different atoms?
Yes, so is sodium chloride, and sodium chloride is not a molecule.
What is salt then?
Covalent bonding. A molecule is covalent bonding. If you have unbalanced dipole moments, that creates a polar molecule. Let me give you some examples. I'm going to kind of like I'm going to cheat a little bit here. I know we've got class is over, right?
Yep.
Okay. Can I just show you something really quick? Okay. So let me just show you. Approximately 109.5. Aren't these all equal bonds? What's more electronegative, carbon or hydrogen? What's more electronegative, carbon or hydrogen? Look on your things. Okay? Carbon, right? Right? Now they're all around at the same. That's a symmetric molecule. You see that? They're all symmetrical. They're symmetrical. Yes? All those moments are directed towards the center of the molecule. Right? And there's 4 of them, and they're all equal angles around. Is there going to be an unbalanced dipole moment there? No, it's not. You have no unbalanced dipole moment. So this is a non-polar molecule. A non-polar molecule. Because those dipole moments are balanced. Think of it like this. You can look at it like this. Look at it visually. Okay? H, C, H, 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 right? These two balance. These two balance. You can look at it like that if you like. Although it's not really true, but in 2 dimensions, we can cheat a little bit. But they're balanced. So it's non-polar. So, let's wrap up. You can have a polar bond, means you have a polar bond. What doesn't have a polar bond? Oxygen, oxygen, if the elements are the same, right? Yes? So you have polar bonds, yes. Then you can have a molecule with more than one bond, yes. And if those dipoles aren't balanced, what? You get a polar molecule, correct? You get it? You with me? You sure? You positive? Okay. Now, you have particles, just let me end here, because this might be confusing. So ionic compounds are not molecules. They're called formula units. Ionic compounds have formula units. So read through bonding. I've done a lot, actually. I've got to do some work with hybridization. It'll make things make more sense. Okay? But that's basically, those are the underpinnings. That's the connection between periodicity and bonding. And it all has to do with differences in electronegativity creating these dipoles and whether or not they're balanced. Okay? We're off. Yeah, it's just low battery. It's okay.